a new topic, namely reciprocity and interreciprocity in linear periodically time varying networks. Okay. So, when we were discussing time invariant networks, we already have seen and understand what these terms mean. So, quick recap of what we did in the time invariant case, so that we can proceed in pretty much the same manner in the time varying case. So, this is an LTI network, and let us say this only consists of R, L and C, and if you drive it with a current I, and we observe this is I1 and this is V2, and all these refer to phasors at this, they are all obviously at the same frequency. And if you take this is 1 prime and this is 2 and this is 2 prime. Now, if we took the same network and interchanged the location of the excitation and the response, so this is I2 hat and this is V1 hat, then by reciprocity V2 by I1 equals V1 hat by I2 hat, all right. And if we had the network had control sources inside, we know how to make this still hold. What you would do is this is the network N and this is the network N hat. You would basically, we derived rules which would basically make, we can make N hat given N which has control sources, right. So, for the time being, let us just stick to networks with simply R, L and C, and this is how this is the result. And how did we write this? Well, quick sketch of the proof. We wrote the G matrix of this network N, right, and then we are exciting it. We arbitrarily number the nodes. Say this was chosen to be ground. Any one of these nodes can be chosen as our reference. So, this is ground. This is node 1, this is node 2 and say this is node 3, and the first job is to actually find the node voltages inside the network. So, G, we write the MNA matrix, that will be G, this element G times the input, that means times the voltage vector, that is basically V1, V2, V3 etc. must be equal to the excitation vector, and that will simply be I1 is going into node 1 and all the entries are 0, correct. So, if we call this vector V, then what do we see? We this vector V, which is given by V1, V2, V3 and so on, is simply G inverse times input vector, right. So, that is basically I1 0 0, right. So, therefore, if we want, so we sorry, I think I am going to call this VO2, not to get confused with so VO2 by I I1 I will call this must be VO1 hat by I2 hat. So, this is going to be I1 and similarly this is going to be I1. So, our output VO2 is nothing but V2 minus V3 and therefore, this is nothing but zero, 1, minus 1 and all zeros times the vector V, right. Remember that V is this guy over here, right. Okay. So, therefore, VO2 over I1 is nothing but 0, 1, minus 1, 0, blah 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 times G inverse times 1, 0, 0 and all zeros follow. All right. So, you can see what is happening. This is the excitation. This is the M&A matrix of N and this is the response, right. All right. Now, this is a scalar, this is a number, correct, which simply relates VO2 to II1. Now, right. Now, this can, because this is a scalar, can as well be a scalar is the same as its transpose. So, this is the same as 1, 0, 0 times G transpose inverse times 0, 1, minus 1, 0, blah blah, correct. So, now you can interpret this expression, right, as taking a network n hat whose M&A matrix of n hat, right. This is the, you can interpret this as being the excitation of a network n hat, right, whose M&A matrix is the transpose of the M&A matrix of the original network, and the excitation is that vector and this is the measurement or result. all right. So, if you do this, then if you draw the circuit corresponding to this is n hat, right, and the excitation is, I mean, the excitation is between, remember this is node 1, this is ground, this is node 2 and this is node 3. The excitation is between nodes 2 and 3. Okay. So, that is the interpretation of that vector there, and the measurement is basically saying it is the voltage. We are finding all the node voltages and we are measuring just the potential of node 1. So, this therefore, so if this is I 2 hat, okay, this is going to be V O 1 hat. Okay. And what this is telling us is that we have interchanged the location of the excitation and the response, and the transfer function remains the same. Now, the key point is that n hat is the interreciprocal or also called the adjoint network. All right, and this network is formed. Remember, how do we get G? G is simply the sum of MNA stamps of the individual elements. And now n hat is the transpose. So, in other words, to form n hat, you basically replace every element by an element whose MNA stamp is its transpose. So, if you have a 2-terminal element like a resistor or a capacitor or an inductor, they all remain the same. With controlled sources, you flip the orientation. We have seen how to derive them, right? Okay. So, this is how we did this in the time invariant case. Now, let us see what happens in the periodically time varying case. Again, to begin with, we will restrict ourselves to networks with so this is LPTV at Fs, okay, and again this is node 1. I will choose this to be node 0, this is node 2 and this is node 3. I will excite it with an input current which is e to the j 2 pi f t, all right, and I will measure the voltage at the output, and the voltage, as you know, is not only consists of f, but all components which are variable. So, this is h sub k of j 2 pi f e to the j 2 pi times f plus k f s times p, all right. Now, suppose we are interested in finding h naught, right, h naught of j 2 pi f, okay. So, is nothing but the ratio of, so this is that, let us call this, this is nothing but V O 2 of t, right. So, is nothing but the component ratio of the output at the frequency f to the input current at frequency f, sorry, this is, yeah. So, right. So, the output at f will be some h 0 of j 2 pi f times e to the j 2 pi f t. The e to the j 2 pi f t in the numerator denominator goes away, and this is basically the ratio. Again, there is not much of a difference. It is just simply the ratio of the phasor corresponding to the frequency f in the output to what we apply in the input. And as I said, we restrict ourselves to networks with R periodically varying R and fixed inductors and capacitor, right. And a special case of periodically varying R, as we have already seen in this course, is periodically operated switch. Okay. Now, this is the transfer function h 0 of j 2 pi f is what we are interested in. So, how would we find that out? Well, again we will write the M&A equations. Now, what do we when we write the G matrix, again we get a set of equations. So, we will write the M&A equations. So, G times the V matrix, right. The V matrix itself now consists of each V is basically a column vector, right, which contains information about the strengths of every frequency in that particular node, right. So, let us call that. So, this is V 1, V 2, V 3 and so on, right. And remember, V 1 is nothing but the vector V 1 is nothing but, we assume that there are every node voltage and branch current can be expressed as is a sum of capital K sinusoids, right. So, this V 1 basically will consist of a phasor which is V 1 minus K blah blah blah, V 0 and V 1 of plus K, right. So, this is a 2 K plus 1 cross 1 column vector. So, likewise, every branch current and every node voltage can be expressed by a bunch of 2 K plus 1 numbers, where each number quantifies the strength of that particular tone, right. So, this is so for example, V 1 of minus capital K is basically the strength of the tone e to the j 2 pi f minus capital K times Fs, right. And in practice, this K can be chosen to be sufficiently large, so that the entire waveform is captured with sufficient precision, right. But since we are only worried about a theoretical development here, we will not worry about the practical issues about how large that capital K must be and so on. So, G times the G matrix times the voltage vector is equal to the current excitation, and the current excitation also now we have to, at every node there is there is a current being injected, right, and that current can also be having components which are of the form f, f plus minus f s and so on. So, each current excitation term will also be a vector, right. Yeah. So, it is a column vector. So, let us call this capital I1, and in our case it will be all zeros, right. And what is capital I1? Is simply the vector of components of the current which are exciting node 1, and they are all 0 except for and basically. So, this will be 1, right. So, basically this is the kth or k plus 1th term, right. So, rather than write notation like this, what I will simply a vector which has got a 1 in the k plus 1 term, I am going to call this as 1 sub capital K plus 1, and that is just for us to understand that only the k plus 1th term in that vector is 1, all the other terms are 0, right. So, basically k plus 2k plus 1 cross 1 column vector with zeros except the k plus 1th term, all right. So, and what is G? G is again the sum of the M&A stamps of all the elements, right. And what are the M&A stamp of a capacitor connected between nodes say A and B, A and B? Yeah, very good. So, what will we do? Well, in the matrix you have this is J 2 pi F c, right, minus J 2 pi F c minus J 2 pi F c and J 2 pi F c, right. And what is F? F is nothing but that diagonal vector which goes from F minus k times F s all the way up to F plus k times F s, right. So, this is the M&A stamp of a capacitor, right, and likewise you will have a resistor stamp also, I mean an inductor also will have the will have a similar stamp, right. Okay. And a periodically varying conductance, say this is G of t, right. We will have, we first form a matrix G, right, remembering that G of t is nothing but sigma over L of G sub L of j e to the j 2 pi L f s times t. So, this G of t is a periodically time varying conductance. All right, and these numbers can be put in a matrix like this. So, this is G 0, G minus 1, blah blah blah, G minus capital K, G 1, G 0, G minus K minus 1, right, and all the way down here you get G K, this becomes G 0, right. So, it will turn out that all the diagonal elements are the same, all these elements will be the same, these elements will all be G 1 and so on, and such a matrix is, this is a 2k plus 1 cross 2k, sorry, this must be minus 2k. G minus 2k, G minus 2k minus 1, and this becomes G. All right. So, this is a 2k plus 1 cross 2k plus 1 matrix. All right. And the idea is that if you apply a voltage across A and B, which has got a given harmonic structure, then you multiply it with G and you will get the resulting harmonics in the current waveform, right. So, the M&A stamp of G of t, therefore, as we have seen earlier, is that we have, just like what we did for in the time invariant case, is given by this matrix G minus G minus G and G. All right. Now, so what is H 0? So, how do we go about finding H 0? We first write the M&A matrix of n. We get the voltage vector. I mean, this times the voltage vector is the current excitation vector. As we did with the time invariant case, we will first write V 1, V 2, V 3, blah blah blah, must be G inverse times 1 capital K plus 1, 0, 0, zeros everywhere. So, this will give us, if you solve this set of equations, this will give us the information about all node voltages, and which basically means that at each node it is telling us what the strengths of the various sinusoids are. All right. Now, but we are not really interested in all the node voltages. Which node voltages are we interested in? We are only interested in V 2 minus, we are interested in these two voltages, and remember that V 2 vector and V 3 vector, basically each one of them contains it contains 2k plus 1 components. So, we are not really interested in all those numbers either, right. We are only interested in the k plus 1th component of these nodes. All right. So, what do we do? So, our output, so H 0 of j 2 pi f is nothing but, what do? We should take V 1, V 2, V 3 and so on, and multiply it with a vector 0. This vector 0 is a, this is what kind of vector now? Is it a row vector or a column vector? This V 1 is a column vector, it has to be a row vector with so this is 1 row and 2k plus 1 columns, right. Okay. And so, we are not interested in V 1, we are interested only in V 2, and which component of V 2 are we interested in? K plus 1th component. So, we would have to put here a row vector which is 1 in the k plus 1th term, right. So, but we already have a notation which says 1 k plus 1 is a column vector with 1 the k plus 1th position and zeros everywhere. So, this will then therefore be, if you want a row vector, you have to write the transpose. So, this is 1 k plus 1 transpose. Does that make sense? So, what will be the next term?
Minus 1 k plus 1.
Very good. It will be minus 1 k plus 1 transpose. And then the rest of it will all be zeros. Okay. Now, sorry. No, this is fine. This one we know is nothing but G inverse times the excitation vector. So, this is 1 blah blah blah, right. So, let us write that because it is important, we will write that separately. So, this is nothing but so H 0 of j 2 pi f is this times G inverse times the excitation vector, which is 1 k plus 1 0 0 and so on. So, let us take some time to interpret this. This is the excitation, G is the network MNA matrix, and this is the measurement or response. all right. And because, and this is scalar, right. Now, because it is a scalar, it must be the same as its transpose, and therefore, it can be rewritten as 1 k plus 1 transpose 0 0 blah blah blah. So, this is a row vector again, okay, times G transpose inverse times zero 1 k plus 1 minus 1 k plus 1 0 blah blah blah, and this 0 is a
That is the
column vector.
Otherwise we can transpose.
Right. All right. So, this can be interpreted now therefore, as this is the excitation, this is the measurement, okay, and this is the M&A matrix, can be interpreted as the M&A matrix of a network n hat. All right. So, if you want to draw a picture which depicts these equations, what should it be? Well, we have our network, this is n hat, this is 1, this is 0, this is 2, and this is 3. And where are we exciting the network? Well, the current source is between nodes. So, this corresponds to excitation at node 2, this corresponds to excitation at node 3, and at what frequency are we exciting the network? At f, right, because only the k plus 1th term is 1. So, this must be e to the j 2 pi f t. All right. And where are we making, what are we measuring as our output? We are measuring, this corresponds to node 1. So, we are interested in voltage at node 1, but which harmonic?
That is the k plus 1 means
Exactly, right. So, we are only we are only interested in that k plus 1th term of that node voltage phasor vector, and therefore, this is we are interested in the output at. So, this is VO2 hat, right, and we are only interested in the component at f, right. So, what this is saying is that if you come up with a network, this is also LPTV at Fs, right, and n hat has an M&A matrix that is the transpose that of n, all right. And therefore, if you take such a network and you excite its output port by a current, then this VO2 hat will have H 0 of j 2 pi f times e to the j 2 pi f t plus blah blah blah. Does it make sense? All right. So, if we all right. Now, how do we generate n hat? Well, we take the individual elements that are there, Well, this is the original element, or let me call that element in n. This is the MNA stamp of that element, right. Now, what do we remember that G matrix is simply the sum of the MNA stamps of the individual elements. So, transposing the G matrix is equivalent to saying I will form a network where I replace each element in the original network by an element whose MNA stamp is the transpose of that of the original. So, if I transpose the MNA stamp, what will I get? F is a diagonal matrix. So, if you transpose it, it remains the same, and therefore, that will remain so j 2 pi f c minus j 2 pi f c minus j 2 pi f c and j 2 pi f c. See, the interesting thing is that when you transpose it, now remember all these are matrices, I mean they are not numbers, all right. So, when you transpose it, you must not only in this case the f will get transposed, and even though in this case in the case of a capacitor things look pretty harmless, this guy, where will he go in the transpose? When you take this MNA stamp and transpose it, where will he go? So, not only are you transposing the blocks, in the block also you must transpose the matrix, right. Fortunately for us, with the capacitor, because everything is diagonal, there is no real issue, right. So, this is going there, and this fellow is coming here, but fortunately F is a diagonal matrix, and therefore, we have no issue. So, what is the element which corresponds to this MNA stamp, therefore? So, this is the MNA okay, and then therefore, we need the element in n hat, and that also happens to be the same capacitor connected between the same two nodes. Okay. Inductor also is the same thing. So, there is no so I am not going to do the math here now. So, this is A, this is B, and in the adjoint or the interreciprocal network, you will have this is A and this is B, this is L, this is also L. now comes the interesting part. So, what other elements do we have? We have periodically time varying conductances. So, this is A, this is B, and this was G of t. And what is the M&A matrix of this character?
G naught if we make it as
A, B, this is A and B. This is that matrix G, this is minus G, this is minus G, and this is plus G. And recall that G matrix is the 2k plus 1 cross 2k plus 1 matrix, which is G 0, G minus 1, blah blah blah, G minus 2k, this is G 1, G 2k, this is G 0. All right. So, this is the M&A stamp. So, we need to transpose it. What do we get there? This is A, this is B, A, this is B. So, if you transpose the M&A stamp, what would you get?
that is a G transpose.
You had to transpose this. So, this is G transpose, all right, and
G transpose.
this is minus G transpose, and that minus G transpose is not transposing of this matrix. It is basically this guy is going there and is getting transposed, right, and likewise, let me write this in red. This is minus G transpose and this is G. Okay. So, this corresponds to a conductance. So, G transpose is basically G 0, G 1, G 2k, this is G minus 1, G minus 2k, G 0, blah blah blah. All right. And remember, G of t, I think we have already done this in the earlier class long ago, is sigma L G sub L of e to the j 2 pi L f s times t, right. So, G of minus t therefore must be sum of L G sub L of e to the minus j 2 pi L f s times t. So, so basically this is saying that if I flip the G of t waveform in time, right, then whatever was G, the first Fourier series, the strength of f s in G of t will become the strength of minus f s in G of minus t. So, this is equivalent to saying, I mean this is equivalent to saying sum over L of G of minus L e to the j 2 pi f s, sorry, j 2 pi L f s times t, right. Okay. I mean the do you get this? Because this G sub L, I mean if you change L to something else uniformly, it remains the same, correct. So, what is the element therefore that corresponds to this M&A stamp? It basically is G of minus t. all right. So, the key difference between a time invariant network and a periodically time varying one, even if the network has got only resistors, inductors and capacitors, is that the time variation of the periodically time varying conductances must be flipped in time. So, for example, let us say you had a switch in N which was controlled by some phi of t, which did so let us say this is t is 0, this is t equals T s, all right. Now, what would the so in n hat you would have the same switch controlled by phi hat of t. So, this is phi of t, right, and phi hat would basically look like this. All right. So, this is t equals 0, this is t equals T s, all right. So, if you have multiple switches, you basically do flip for everything, right. So, to summarize, therefore, we have an original network N, that is LPTV at F s. We excite it with a current e to the j 2 pi f t. We get a voltage at the other port, which is h 0 of j 2 pi f times e to the j 2 pi f t, plus a whole lot of other terms, right. What this is telling us is that what this is telling us is that you interchange. So, this is 1 1 prime 2 2 prime, you excite the second port of the adjoint with e to the j 2 pi f t, and what you will get is the same h 0 of j 2 pi f times e to the j 2 pi f t plus a whole bunch of other terms, right. And how do we go from n to n hat? So, n hat is derived by element wise replacement of every element in n, right. C and L, so linear, as long as they are linear, and time invariant. Let me write that away. L and C remain unchanged. All right. Periodically time varying conductance, right, is replaced by G of minus t. All right. Okay. Now, this basically explains, I mean basically discusses reciprocity networks with only with time varying resistors, inductors and capacitors, right. We have to take a look at control sources tomorrow.